section 4 was the ugly section, the actual definition of a limit, so the epsilon delta stuff. Section 5 was continuity, and section 6 is what we're covering the next 3 days. So I will give you a review on Thursday, quiz on Friday covering that stuff. So if we are talking now about two different things here, limits at infinity and horizontal asymptotes. We have calculated limits where we get infinity for an answer. You know, the limit as x approaches 0 is infinity or negative infinity. But what we haven't done is found a limit where I said let x approach infinity and tell me what this is equal to. So that's the piece that we're looking at now. This is just a picture to show you what's going on here. So if I ask for the limit as x approaches infinity, sometimes these exist, sometimes they don't. I put 3 different pictures up here where a limit at infinity does exist. If you have, what would this pink line be considered if it's something we're getting closer and closer to but not actually touching? It's an asymptote. When you have a horizontal asymptote, then your limit as you approach infinity or negative infinity will equal that number. The one change that we're going to see back in college algebra when we did horizontal asymptotes, we never had more than one. We were just graphing nice rational functions, and it was always just one horizontal asymptote that both ends approach. It is actually possible, depending on the equation, to have multiple horizontal asymptotes. So we might have one as we approach positive infinity and a different one as we approach negative infinity. So just something to keep in mind there. So if I have a function defined on an interval at negative infinity to a, this is just showing these limits are at approaching negative infinity. So you can have the positive or you can have the negative. Okay. Would this one have a limit as you approach positive infinity? Not an actual number. If that keeps going up, what would it be? Infinity. So you can have infinity for an answer on these as well. So you have a horizontal asymptote if either the limit as you approach positive or negative infinity equals that number. Okay. One example that would have different horizontal asymptotes is arctangent. Arctangent, you guys remember that, right? It's the inverse of tangent. We remember the graph of tangent looks like this. The inverse is when you flip it on its side, and it looks like this. And so you can see that it had one limit as you approach the positive infinity and another as you approach negative infinity. So that's just one particular example where you could get multiple asymptotes. So let's look at a graph and see if we can answer these. Maybe. So I'm asking you to give me a bunch of different things from this graph. Infinite limits. That's the limit as you approach positive, or as where you get a positive or negative infinity for an answer. Limits at infinity, those are the limits where you approach positive and negative infinity. And any asymptotes. So infinite limits. Are there any numbers where if I approach them, I would get positive or negative infinity for an answer? Okay, as x approaches what? This is my x and y axis here. So where is my graph going to positive or negative infinity? Okay, when x approaches 2. from both sides, or would I have to do them separately? Separately. So we could do the limit as x approaches 2 from the left. So if I'm coming into 2 from the left, where's my graph going? Negative infinity. As I approach 2 from the right, where's my graph going? Positive infinity. Okay, there's another one. This one I don't have to split up because from both sides, as you approach -1, where's the graph going? Infinity. Okay, so those are my infinite limits, where you get infinity for an answer. What happens at these? What kind of asymptote? Those are vertical asymptotes. So when you get positive or negative infinity for your answer, that's a vertical asymptote. So I have them at x equals -1 and x equals 2. All right. Limits at infinity. We have two options. We can do the limit as you approach negative infinity and the limit as you approach positive infinity. So as my graph goes forever in the negative direction, is it approaching any one number? 2. You see this is flattening out at a y value of +2. So as my x goes to negative infinity, my graph is going to 2. As x goes to positive infinity, is it approaching anything? 4. See right here. So what's going on at 2 and 4? Horizontal asymptotes. Vertical are x equals, horizontal are y equals. So your limits at infinity and your infinite limits are telling you where those asymptotes are. Questions for me on this? So let's look at some functions. Limit as x approaches infinity of 1 over x. 1 over x, that was one of our graphs in college algebra that we did transformations to. What did it look like? What do you do if you don't know what it looks like? Other than stare at the wall. What? Make a t-chart, right? If I put in a -1, 1 over -1 is -1. If I put in a -2, 1 over -2 is -1/2. -3 would give me a -1/3. What happens if you put in a -1/2? 1 divided by -1/2? -2. Flip and multiply. So -1/2 gives me -2. Is this looking familiar? If you put in a +1, 1 over 1 is 1, 1 over 2 is a half, 1 over 1/2 would be 2. Or 1 over x look like that. So from this, my limit as x goes to infinity would be what? My x is going forever in the positive direction. Your limit is asking what your y is getting close to. 0. The limit as x approaches negative infinity. So as we go forever in the negative direction, my y is getting close to 0. So how many horizontal asymptotes does this one have? Just one. Y equals 0. I didn't ask for it here, but you could have given it to me. We have one horizontal asymptote. Okay. Your book lists this as a theorem. I don't know if we even necessarily need it as that, something that we might know. We've talked about 1 over x and 1 over x squared before. But if you have 1 over x to any power, so 1 over x squared, 1 over x cubed, 1 over x to the 4th, as you go to either positive or negative infinity, your limit is always going to equal 0. And if you think about that, it's because when you plug in, what's the one number you can't put on the bottom? 0. It's giving you a horizontal asymptote there. All right. Now let's talk about how in the world I would evaluate something like this. Because that's a little bit uglier. That's just not 1 over x. We could graph it, but is that something I can count on the test? No. So I have to have an algebraic way of getting there. What we can do is manipulate this equation to get something that we can simplify. So on these problems, if you have a polynomial divided by a polynomial, our strategy is going to be to divide the top and bottom by the highest power of x. What's the highest power of x? X squared. So we can either take everything and divide by x squared, or if you prefer, you can think of it as multiplying by 1 over x squared. We know that algebraically, as long as we do it on the top and the bottom of the fraction, it's legal, because they would cancel each other out. So I'm not changing my problem. Okay, if I distribute this, what's 3x squared divided by x squared? 3. Minus x over x squared. What's that reduced to? 1 over x. Minus 2 over x squared. That doesn't reduce at all. 5x squared divided by x squared is 5. 4x divided by x squared is 4 over x. One divided by x squared is 1 over x squared. Okay, initially it looks like we just made life really hard, but this is actually very good news for us. We know we can do the limit of all these different terms, right? We can take the limit to each piece. What's the limit as you approach infinity of 3? 3. We know the limit of a constant is still a constant. Okay. You could use the theorem we just had for this, or we could just think about it. We're approaching infinity. If I have 1, and I divide it by a bigger and bigger and bigger number, what is that going to? 0, right? If I have 1 cookie, and I split it between just Landon and I, we each get half. If I split it between Landon, Lauren, and I, we each get a third. If I throw Maddie in, we're getting a fourth. As I add more people, we're getting less and less of that cookie. So it's going to 0. What about 2 over x squared? Still going to go to 0. If you have a number over infinity, it's turning into a 0. Okay, 5 is a constant, so it's just going to stay at 5. 4 divided by infinity is going to 1 over infinity squared is going to. So what's this whole thing turn into? 3/5. That is my limit. That is the horizontal asymptote. in college algebra, we graphed rational functions, and I just gave you these rules for horizontal asymptotes, and I said you had to learn them. And I just said, if the degree of the top is smaller, it's always 0. If it's the same degree on top and bottom, we divided the leading coefficients. Do you remember those? This is why. I couldn't show you this explanation then because you probably would have cried. But this is why, because of the calculus. That's why it works out that way. Questions on that? So let's just keep practicing. We're going to try some ugly ones, try some nice ones. We're just going to try to simplify these limits today. Horizontal and vertical asymptotes in this. How do I find vertical asymptotes? Right. So do I even really have to do any calculus for that? No. If you have a fraction, the vertical asymptote is x equals whatever makes the bottom 0. So if you set that equal to 0, my vertical asymptote is 3/5. Graphically, what that looks like is as you're approaching 3/5 from the left or the right, it's going to either positive or negative. 5/3, yes. Something like that, right? About 5/3, that's better. So that's where your graph is going to positive or negative infinity. Horizontal asymptotes are basically the limits as you approach positive and negative infinity. I will say, in Calc 1, most of our problems are going to be nice. So your limit as you approach positive and negative infinity, probably 95% of the time they will be the same number because I'm giving you fairly nice ones. But haven't we seen a graph where they approach different numbers? So can I just do one and assume it's the same? No, I am going to make sure you check both. So on test or quiz, point values are assigned for both the positive and the negative. Even though I'm telling you, most of the time they're going to turn out to match. We have to do both. So as I do the limit as x approaches infinity of this. Alright, so on the last problem, our strategy was to divide top and bottom by the highest power of x. We're going to stick with that, but we have to think a little bit harder this time. I have an x squared, but it's under a square root. So what power of x is that really? It's like x to the first, isn't it? The square root of x squared is x. So I really have an x to the first on top and an x to the first on the bottom. So we have to take it times 1 over x on top and bottom. Okay, these things have to be equivalent. Now on the top, if I just do that x, can I bring it under the square root? No, so how should I? We can think of this as the square root of 1 over x squared. Okay. These two things have to be equivalent. Because I need to bring the first one under a square root, that's why I did it as the square root of 1 over x squared. But a square root and a square would cancel, so it is equivalent to 1 over x. So then we have 2x squared over x squared. Since they're both under the square root, we just get to simplify them. So 2x squared over x squared is 2. 1 over x squared. On the bottom, 3x divided by x would be a 3. 5 over x. Now we're just essentially plugging in our infinity. If it's a constant, that stays. So the 2 stays. 1 over infinity squared. A number over infinity always turns into 0. 3 minus 5 over infinity, so a number over infinity turns into 0. So we just get radical 2 over 3. Am I done? I need to do the limit as you approach negative infinity. Okay. I did this one as our first example intentionally. If I start out the same way as before, I actually have a slight problem. If you're going to negative infinity, 1 over a negative number is going to be negative. 1 over a negative squared is going to be positive. So are these two things equivalent right now? What do I need to do to one of them? Put a negative on the front. Okay, I had to do one right off the bat to show you that you could get different answers here. So that square root is what's causing that. So now if we simplify this, okay, I'm just going to keep my negative out in front. Basically divide each of these terms by x squared. So 2x squared over x squared is 2. 1 over x squared. 3x over x is 3. Minus 5 over x. So now if we plug in our infinity, 2 stays. 1 over a negative infinity squared is 1 over a really big number, so that's turning into 0. 3 minus 5 over a really big negative number, that's still turning into 0. Whether it's a number over positive or negative infinity, it turns into 0. So this gives me negative radical 2 over 3. So how many horizontal asymptotes does this one have? 2. Y equals a positive radical 2 over 3, and y equals a negative radical 2 over 3. So that's why you have to check both. Questions so far? Just keep working progress. Look at this one. If I just plug in infinity, is it going to tell me anything? I've just plugged it in. If it were a number, we could probably plug it in. But do I know what that equals? No. If those were added, then would we know what they equal? If you take a really big number and add a really big number, what do you get? A really big number. So if those were added, then it would go to infinity. But the subtraction, we don't know. That kind of gets into a huge mess called degrees of infinity. which you wouldn't learn about unless you went on to major in math. But if you have infinity minus infinity, we don't know what that turns into, because I don't know which of those infinities is growing larger or growing faster, and if it will give me an actual number. So I can't just plug in here. But think about all the strategies we have up until now. I have a problem with a radical and I can't just plug in. What have we done in the past? We've done a lot of these types of problems. What do we multiply by?
The conjugate.
The conjugate. This is just over 1. Our strategy with radicals all semester has been, if we can't do anything else, let's multiply by the conjugate. So when I do that, square root of x squared plus 1 times the square root of x squared plus 1. Those radicals drop. You get x squared plus 1. Nice thing about the conjugate, the outside and inside always cancel. And we have our minus x squared on the end. On the bottom we have the square root of x squared plus 1 plus x. What happens now?
X squared on the top.
Mm-hmm. Okay, so now, could I just plug in my infinities? We have a 1 on top. On the bottom, infinity squared plus 1, that's just a really big number, isn't it? Plus infinity. If you're adding infinities, you can assume it goes to infinity. So 1 over infinity, 1 over a really, really big number, gives me 0. Anytime you have a number over infinity, or infinity squared, or infinity plus infinity, as long as the bottom is going to infinity, it's just 0. I am not going to do example 6. I think I'm going to skip that one. We're probably not going to get too much into the trig functions. Let's maybe do just a couple more and then we're going to stop for today. So what's the limit as x approaches negative infinity of e to the x? So if I just plugged in, I would get e to the negative infinity. What does a negative exponent do? Changes force, right? Drops it down to the bottom. So 1 over e to the infinity. Alright, if you take a number to a bigger and bigger power, what's that turning into? Really big number, isn't it? So this is really just turning into 1 over infinity, so that would be 0. Okay. The limit as x approaches 0 from the left of e to the 1 over x. Let's see if we can figure this out. We've talked about 1 over x already today, haven't we? We graphed this earlier. We said the graph looks like this. As you approach 0 from the left, what's 1 over x going to? So this is really just e to the negative infinity, which is 1 over e to the infinity, which is 0. So we can use some reasoning to get us through these. Last problem for today. Limit as x approaches infinity of sine x. We've graphed sine. We did that at the very beginning. Remember that trig handout I gave you and said you might want to keep this handy, put it in front of your binder. What's the graph of sine look like? Yeah, just that nice wave. It keeps bouncing back and forth between -1 and 1. Does it ever stop? No. So as it goes on to infinity, does it approach any certain number? No, it just keeps bouncing back and forth. So what would my answer be? Just bouncing back and forth there. Okay. This is our stopping point for today. If you look at the very end, I put the homework on here. I am removing one problem. I don't want to take off problem 11. Technically, guys, I have taught you everything that you need on this already. Tomorrow we'll finish the notes, but you truly have everything you need to do all the book problems right now. Tomorrow I will give a look at a handout as well to practice some more, so that will be probably in class. We might do that. So these book problems will be due on Thursday. So really tomorrow I will probably finish the notes. We'll do some more practice. We're probably looking at a work day on Wednesday. So you don't have to get too gung-ho and jump all in with this. You're welcome to get started on it. I would encourage you to do a little bit, but we will have class time to work on it later on this week. And you do have some time right now to start.